Well, good afternoon, everybody. Welcome to our session on deep learning and AI at scale for managers. 3 questions at the beginning. How many of you are already using big data? Everybody. How many of you are curious to get started in deep learning and AI? All right. How many of you are managers? About 90%. All right. Very good. So my name is Vladimir Bacvanski. I'm dealing with big data for a number of years now. I'm a founder of a company, SciSpike. We do projects where we develop highly scalable web applications. The systems typically have big data backends. Our applications are typically these days in the area of Internet of Things. We are receiving a lot of data, like in patient monitoring, also various systems for smart cities, where we are collecting a variety of data. And partly what we do is big data analytics on these, but also we are now trying to learn new things from this data, and this is the space where we apply some of the deep learning techniques and integrating with some of the AI techniques. So we are going to talk today about these techniques at the level which is above the usual business talk, like deep learning and AI. It is good for you, it is good for the business, but it's also not going to talk about the configuration of threads of your machine, which may be too detailed. So first of all, the distinction between AI, machine learning, and deep learning. So let's start with AI first. So what is a good definition for AI? My favorite is, if it works, you cannot call it AI anymore. And in the past, it was considered a magical feat. You have a program that is written in some high-level computer language, and that gets translated to assembly code of a computer. That is amazing. That is artificial intelligence. Today, we have a voice recognition and so on. So artificial intelligence has its relatively humble beginnings in the 50s, going beyond ordinary computations and calculations. And we have seen various algorithms, like searches in problem spaces, playing various games, making decisions, expert systems. And this was progressing for some time. In the 80s, we have seen that we can figure out something out of data that we have. And this is the era of machine learning. Probably spam filtering, various algorithms for classification of data are a good example of systems in that space. So you see, artificial intelligence is a broader area than machine learning. Machine learning started hitting certain limits. We would like it to do smarter things. And there were various experiments trying to introduce systems like neural networks. The idea sounded really promising, but the first attempts were not overly successful. And we have seen the resurrection of this idea around 2010s, where we have the deep learning techniques, and we are able to use something like recognition of objects on images, something that was considered like unimaginable feat in the early days. So even though that the AI is actually the encompassing term, it is often used today as application of deep learning to do something really smart, something that people have been typically doing. So one thing that you need to know when you start dealing with this area, this is the area with a lot of hype. And here is the typical hype curve. And this is a hype curve that is showing deep neural nets. So almost there at the peak. So you need to really watch for the hype. You really need to watch for the propaganda materials of various vendors. But it is a fact that this is a very exciting area, and it is capable of giving us great advantages in our business. The space is getting really busy, quite saturated with various systems. Here is one overview. When you download the presentation later, you will be able to zoom in. It is actually quite a big picture. There are 288 companies listed on this poster. And when we zoom in a little bit, you will be able to see various areas like enterprise intelligence, and then various enterprise functions like customer support and marketing. And you have here the players in these spaces. Over here on the side, you can see that there is a rich technology stack that includes things like data science, things like machine learning, natural language processing, APIs, and similar. And one thing that is very encouraging in this space is that there is a range of different open source libraries. And our usual suspects like TensorFlow and similar Spark, they are listed in this space. I will have later for you certain recommendations, what would be good systems for you to start playing with deep learning and AI after this talk. So it's a very rich space, and we need to start looking what is happening there. Now, looking into understanding of this space, we need to start with machine learning. And there is one standard definition of machine learning, which is saying that this is a study of computer algorithms that automatically improve through experience. And this is the classic definition from Tom Mitchell with the favorite text on this topic. The applications that we have today are in the space of text and speech recognition, various recommendation systems, image classification, understanding is there a person in the image, but also who is the person in the image, and also how does this person feel. So you have the even emotional analytics based on the faces. So a lot of interesting areas where we can apply this machine learning systems. When it comes to machine learning approaches, there are three basic areas. The oldest one is what is known as the supervised learning. There, the hallmark is that you have a labeled data. So you provide the data, and then you say, this is good, this is bad, and then you train the system. So you are providing feedback to the system. And the result of that is that the system should be able to predict the outcome or a future. A much more challenging aspect is unsupervised learning. And the interesting thing there is that there are no labels. You cannot tell the system what is good and what is bad. The system should somehow figure out what are the differences. And the interesting thing here is there is no feedback that we are giving to the system. And the system should somehow find the hidden structure. And you can think that this approach is more similar to how we humans learn. And finally, one of the more interesting approaches is the reinforcement learning. And this is basically an approach that allows you to make reasoning around the decision process. There is a certain reward system that is introduced. So the system is being rewarded or punished for certain choices. And what is interesting here is that the system is capable of learning a series of actions. It is not just simple classifications. So in the press, you have a lot of articles and publications around unsupervised and reinforcement learning. But when it comes to practical uses in industry, according to Gartner, 95% of uses of this technology are supervised learning. And that really makes sense. So in this space, we have seen development of a variety of algorithms. And it is often viewed as some type of a magic. How do you make a decision which algorithm to use? But in fact, there are some meta-reasoning approaches and guidelines how to choose the algorithm for your problem. And I have here borrowed one nice visualization. This is from Microsoft Azure Machine Learning. It's a cheat sheet. Which algorithm should you choose depending on your problem? And this is really a good start depending on what kind of data do you have, what kind of decisions do you need to make. And what I want to say with this is that machine learning and these aspects of deep learning and AI is something that can be learned. You don't necessarily need a genius, but particularly in the area of machine learning, a team member who is familiar with data science can follow some established procedures and create good outcomes for the organization. One interesting thing, and the panelists in front of this session have been mentioning that what is better, to have a smarter algorithm or just to have more data? And one of the really interesting realizations is that big data, more data is often more beneficial than having smarter algorithms. A really interesting quote from Google. And this is quite interesting. So simple algorithm with more data is preferred. And this is actually very good for us because when we work on optimizing our algorithms and getting smarter outputs, it is likely that we can do that simply by providing more data or improving the quality of our data. And as we are applying these models, you should always think about end users and what matters to them. And one thing for the end users is no matter how fancy is your machine learning or deep learning, the users are going to experience that through some type of UI. And this is typically visualization, or it can be speech. The reason why I'm mentioning that is that I see organizations deploy data scientists. They invent some really fancy algorithms and approaches. But what comes out is never presented in a good form to the end users. And then they don't see the value of the approach or the investment. Imagine you're showing this to your CEO and CFO, and they see the output on the terminal. They're not going to be impressed. In particular, you need to work with your end users to provide a real benefit that they can immediately experience. So going from a machine learning into the deep learning. So the approach here is that with deep learning, we have an approach that is using neural networks. And the neural networks have been around since the 70s. In the 90s, there were a lot of experiments, and we have seen the first good applications of neural networks for character recognition and similar applications. But then somehow the research somewhat fizzled out. The benefits for industrial applications were not so frequent, and kind of neural networks were not fashionable anymore. We see recently the neural networks are coming back, and it turned out that if you apply these neural networks with large volumes of data and dramatically increase the units that are doing the processing in these neural networks, we actually can get some good results. So it is interesting that the quantity got transformed into quality of decisions with the neural networks. So in these neural networks, one of the particularly important enhancements was the application of GPUs, the graphical processing units. So if you think, what are they really? They are really computers that can perform a large number of very simple operations. So a simple math, matrix calculations, are a very good choice for GPUs. And instead of them being used for rendering, we could repurpose them to do massive calculations of relatively primitive computations that are calculating matrices, for example. And traditionally, these neural networks, they had very few layers of these computational nodes. And now what we have is when we are using deep neural network, which may have a number of layers, we can present some input as an image. This thing will be shredded into pieces, and the values will be passed into the layers of this neural network. The first layer is going to be the input, receives that, and then it will perform some calculations that will go through different intermediate, or how we call them, hidden layers. And eventually, the last layer will be applying some classification, and we will get the text that this is cat. The interesting and important thing is that we don't need to design the algorithm for recognizing if something is cat or a dog, but the system is trained how to achieve that. And this is something that is important, because if you think about the algorithm to decide if something is dog or a cat, it is actually quite difficult. If you look at the image, they both have two eyes and the nose and ears, and they may even look quite similar to each other. The systems like this are able to recognize this. The overall architecture in this space is that we have a network that has what is known as the visible layer that is receiving the input from our data. And then there is one or more so-called hidden layers. And then eventually, the output layer is going to do the classification, clustering, predictions, and the output that we really want to use. Now, the question is, how many layers do we have as hidden layers? And in many systems, you will find that the number of hidden layers is 1 or 2. That is sufficient, actually, for most applications. In literature, you can find systems that have 3 hidden layers are referred to as deep layers, very deep, over 16, and a rarity are extremely deep layers of 50 or even 1,000 layers. But in practice, small number of layers are often sufficient. Now, you can see here that there is some data that is going between these different nodes. And each of these nodes represent a function that is transforming the data. And these functions will have a number of parameters. The secret of training neural network is how do we adjust these parameters so that we can converge to some solution. And these things are called hyperparameters. And then you are going to enforce some results, amplify some, you are going to attenuate the other ones. And that is actually one of the art of constructing the neural network. And in the design of the neural networks, you will find several different architectures depending on the layers and how are they connected. But for the end users, this is not so important. So how are we going to apply this type of systems for our applications? So first of all, we need to have some examples that we prepare. So we create a model. Often this model is going to be labeled. So we will train the system, let's say with images. We will present 1 million images of cats, 1 million images of dogs, and we know which one is which. Then, for the functions that are doing the processing, we will start with some random set of parameters. So you don't know at the beginning what are the right values. So you start with a random set. And then you are going to try to classify the image, and then you will measure the known values against the output. And you will see how does that work. Normally, this is never going to work well from the first pass. So then we will go and modify parameters, and then we will try to improve the match. And this is actually where different neural network algorithms and architectures differ. How do we choose parameters? How do we change the values of parameters? And then we will retry, and we will go through a number of iterations in trying to improve the match. And this is the tricky part. So this is where you have a variety of designs. And sometimes you will find that a particular neural network architecture simply does not respond well to your data set. And then you will say, well, let me try this other model. This other model also looks promising. And this is one of the key things. You don't get a guaranteed result. Instead, you often need to try a variety of different algorithms. And the good thing is today is that in the literature, it is already known approximately which of these algorithms are good match for what kind of problems. And after certain training, you will find that the model can eventually make useful predictions. To give you another example, when you start playing with this at home, one of the really good exercises is so-called the MNIST data set. And this is the set of handwritten numbers. And the system is trying to classify the numbers, so basically to do the recognition of the number. So you try to run this on your PC, and in order to get accuracy of 99.2%, you may be running and training this data set for about 20 minutes on your desktop machine, which is, let's say, Xeon 6-core machine. But if you switch to a GPU, so for example, if you run this on NVIDIA Titan X GPU, which is kind of upper range GPU that you can get for home computers, it has 3,500 cores on this GPU. Your training time is going to be reduced from 20 minutes on 6-core Xeon, this is like 4.3 gigahertz, to about 20 seconds. And this is the big difference that the GPUs are making. And considering you as an experimenter or the learner, going with GPU allows you to run many experiments within time, and you have the shortened cycle. And today, such GPUs are available not only if you are running something on your local machine, but also if you go into the cloud. Google and Amazon, they have Tesla GPUs from NVIDIA. But you need to be really careful about the cost. If you are planning to spend some time studying this deep learning, it may be much cheaper to actually buy the machine or build it on your own than to actually rent it from the cloud. These are quite expensive high-end machines. One rule of thumb is saying if you plan to study this for 3 months, it is cheaper to buy or build your own machine than to do it in the cloud. All right. So this is the idea. This is the overall process for training and using these neural networks. And in the meantime, we see a number of different systems that enable us to do this. TensorFlow from Google is the most active one, the most popular one. Very easy to start and nicely packaged. You program it in Python. Recently, there is a layer on top of it, which is called Keras. Keras will simplify the use of this even further, and it's an excellent vehicle for you to start. And there are a number of others. You know, some of them are internally C and C++ and provide the Python wrapper, so you can very easily construct your examples. Some of them are using Java as a dominant language, like deep learning for J, so you have quite a bit of options. But TensorFlow seems to lead the pack. So we talked about the layers and having these hidden layers that are actually quite useful. So here is one example of how these hidden layers help in image recognition. So for example, in the first layer will be trained to recognize lines or elements of shapes. And then you will have the layer 2. Layer 2 is going to combine certain elementary shapes into some patterns. So for example, we can recognize that there is something that looks like an eye, and there is something that always appears that looks like this. And it is often going to be combined with the element like this that we recognize as nose. So the system recognizes certain patterns in the layer 2. And then finally, layer 3 is going to assemble those, and it will start recognizing some human features. And you can imagine, you can fine-tune that even more, and you could even train the system to recognize certain people based on these characteristics. So 3-layer model that is capable of recognizing people. In a similar way, you have the voice recognition, where you are getting voice signal. Then that will be transformed. For example, the noise in the background will be eliminated. The human voice will be extracted and purified, and eventually that will be recognized as some type of text that person is speaking. So these multiple levels are key for the deep learning to be able to recognize more complex things. So basically, when we are working with these deep learning systems, what is happening inside is that you have layers that will do some computation of a number of these functions, and the result will be fed into the functions that exist on the next layer. And the model is defined with very simple mathematical equation. And the key thing, you see these little things with arrows, they are called tensors. And you can think of a tensor as an n-dimensional matrix. So it is basically, we have the ability to reduce the deep learning to mathematical computation of matrices that are n-dimensional matrices. And this is where the power of GPUs comes so handy. So you're thinking now applying this deep learning. The approach has advantages and disadvantages. The big benefit is that the whole thing is really conceptually simple. We are training the system is going to adjust the hyperparameters. It starts with some random values, it will be trained, and eventually we get the right result. The system is also very flexible, so it is capable of recognizing a voice or images and a variety of data. So it is really agnostic when it comes to the data source. And one of the things that is really nice about this approach is that you start with one system, and you would like to improve its accuracy. You can keep the same model, and then you feed it more data, and the system will improve over time. And this is actually a very fascinating capability, because you can put the system in production, the system runs. As the system is running, you can provide it with more data, and the system will improve its accuracy over time. That's a great benefit. And notice that this fine-tuning and improvement of capability is actually happening without necessary involvement of developers or programmers. So there is no human labor that is invested in improving the results. And then you have a nice positive feedback loop. And the area that these systems excel is pattern recognition. And this is really good because this is the area where we have other approaches where humans define algorithms that cannot do good recognition of patterns. On the other hand, there are a number of drawbacks. You know, usually you hear about the advantages and how fascinating this all is, but there are also a set of difficulties. So it is very difficult to interpret. So you have a system that you have trained, and you ask somebody to understand and explain. So how does this work? You don't have this transparency. The system has been trained, and it basically functions as a black box. The systems are slow to train. You need to expect to train the system with lots of data, and that takes considerable time. Some systems can be trained in hours. Some systems are trained for weeks on very large clusters. When we say may overfit, that means that the system at the end recognizes only the input data set that has been used for training, but when we present it with some other things that were not in this data set, the system will misclassify them. And one particular thing is the systems are data hungry, so we need to provide them with lots of data for training. And that is interesting. If you just start in some new area, it is very difficult to start if you don't have enough data. So we have one project, which is quite interesting, in which we are doing application for Internet of Things in automotive space. And we would like to react on changes in acceleration in cars. So you may detect that there is some debris on the road or accident just following the signals. But when we are just starting, you don't have enough data, and it is very difficult to provide the results. So you need to collect the data for a while before you can go and train the system. Now, all of the systems that we have seen on this list are primarily designed to run on single machines and GPUs, but there is also a very attractive proposition to expand that. And we are here at the Big Data Conference. So naturally, there was the hybrid solution where we are trying to combine the big data and the deep learning approaches. And over time, there are a number of approaches that are typically merging Spark with some of the data deep learning algorithms. And that is kind of a natural choice, particularly when you're looking into the data storage in HDFS or in the cloud. This is a distributed storage. And then we have the machines that are distributed. Well, the idea is to add functionality like a TensorFlow into the Spark nodes, and then you can do the machine learning on these nodes. So basically split the processing across the nodes. And this is just one example, TensorFlowOnSpark. There are a number of other projects. And what is interesting about these approaches is that when you have, let's say, a regular TensorFlow application, and it works, and you figure out, OK, now let us go and process even more data. We are going to the Spark cluster. There are very few lines of code that you need to change. So in this example, it's only about 10 lines of Python code that you need to change in order to run this on Spark Cloud. One question that I want you to ask yourself. So you're thinking about rolling out your deep learning into a distributed platform. The key question that you need to answer is, do we really need to do that? There are some interesting things. So there was an example of machine learning at Quora. And they have been running machine learning on 15 machines running Spark, and the processing took 6 hours. Somebody came to the idea, well, how about we prune this data set? We get rid of all the columns and attributes that we don't need, squeeze it so that it fits into one machine, and then find somebody who will write a decent C++ program to process that. And the outcome was 10 minutes processing on one machine. So if you can squeeze the stuff into one machine, always try to do that. It is going to be faster. But also, we have seen some really good results with TensorFlowOnSpark. Databricks reported on a 13-node Spark cluster versus single machine, 7 times improvement. So you should never trust these benchmarks. You should always try it out for yourself on your data set. But the practice of pruning the data set, reducing the data is highly valuable as a way of cutting the development time. So try to reduce your data set. Sometimes you don't really need to process everything, but smart sampling could be good. And finally, always benchmark the systems with your data set. Now, when we look into this emergence of deep learning and AI, think about which type of systems are going to produce the largest amount of data. And we see these are the Internet of Things systems. So we are getting huge volume of data from this Internet of Things systems, and it is naturally to feed that into some deep learning or AI systems. As an example of such application is something that is called ambient intelligence. And this is a slide from the lab at Stanford. So here we are doing ambient intelligence, where we have some space in which we have humans. The system is capable of figuring out who is that in this space, what are they doing. And you can be using the deep learning and AI systems to recognize the activities, recognize what would be the next things that these actors in space would like to do, and then we provide some additional service to them. So we can help them in their activities. We can do something for them ahead of time. And one of the common applications that you see these days is in smart homes. Somebody enters the home, or the system knows the owner of the house is coming home at a particular time, and the system learned that, and then it may turn the heating on and similar. So very, very interesting area. And that brings us to the next point. You see, with Internet of Things, you have sensors, and then you have the system. And the question is, where do you put your AI? Do you put it close to the sensor? Do you put it at the back end? Very important question. Imagine what can you do when you put your AI close to the source of events. Imagine if you have video feeds. So when you put the AI close to the source of the event, you may decide, are you going to send all of this data back to the server? Imagine if you have a video feed, this is going to result in quite a bit of network traffic. And imagine in some system for, let's say, a smart city, perhaps you can have a video camera that is monitoring highway, and the camera can send the information. There was an accident. So the camera could recognize such things instead of us shipping gigabytes of data to the server for processing. So you can send only the highly relevant events, and pattern matching, classification, and so on can be done close to the source. In the past, that was very rarely the case. But these days, you even have a various AI and deep learning system that you can run on your phones. So this is now a very attractive proposition to put smartness to close to the sensors. And there are even some AI packages that you can run on Raspberry Pi and similar systems. So preserve the bandwidth and save processing resources. For more serious work, you want to put the AI on the back end, and you would typically use AI stuff that is difficult to do with conventional processing. So pattern matching, classification, recognition, and similar things. But it's important for you as architects to make a decision, where is that going to happen? Now, going back to our business applications, our systems are never isolated. They are always part of some larger picture. And a typical workflow that we see is you have the creation of data. This is happening on devices, or users are creating data. The data is being passed through the network. Then you would typically aggregate this data. You would collect the data. And this is where you would have your typical big data management and storage function. For example, in many of our systems that we implement for our clients, we have the data that is arriving, gets stored into Apache Kafka, or it gets stored into time series databases. Sometimes we put it in Cassandra, sometimes we put it in HBase. There is OpenTSDB, Open Time Series Database. Scylla is another choice. So we managed to store the data there. And this is the place for your analytics with machine learning and AI, and there are various approaches there. So you determine the things that you were not able to do in a conventional application, and this is where you would be able to act and then enhance the behavior. And the interesting thing, particularly in Internet of Things systems, is that your actions that you do here are actually going to impact your environment, and you have actually positive feedback loop. Now, this part is interesting. You have various choices. And for you, you may be thinking, well, when I get back from the conference, what should I do? How should I start with that? One of the things that you can do is you can plug in here various components, for example, to detect the objects and scenes, maybe detect people, understand what is the language, or understand what is the text message about. And for that, you can think about an easy start by using some of the cloud-based machine learning services. And here we have Google, we have the Amazon, Azure. All of these have services that are very easy to use, where you can, for example, send a voice signal, and then you will get this voice transcribed as a text very, very fast and very easy to use. Very simple REST call that you will make. You can send images, and very, very easy way to start. And the beauty of that is that you can reap the benefits of machine learning, deep learning, AI, without necessarily being expert in this field. And you will see, if you look at the science project that high schoolers are doing, they are actually already using this in their projects. So you have kids using the AI from these services and creating quite fascinating applications. So it is very easy to start. There is no reason not to. I want to wrap up with a set of challenges. So there is one fundamental issue with AI that is problematic, and this is accuracy. So the systems are not 100% accurate. And the question is, so what is the level of trust? What if you know that your super fancy AI system is only 50% accurate? Then you know you will not rely on it. You may accept the result as a friendly suggestion, but you know it is me who is making the decision. And you're always ready. You're never going to fall asleep. What if the accuracy is 99%? You learn to trust it, and then the system is going to mess up with something. And the question is, what is the consequence of failure? What if this is a self-driving car? You know? And the response that they are still making fewer mistakes that people may not be comforting when you are involved in the issue. So this is a big problem. You know, none of these systems is 100% accurate, and there is even the new area, which is the AI psychology, which is more dealing with people in interacting with AI systems. So we need to calibrate our expectations, and that is going to be quite difficult. So accuracy is a big problem. Deep learning has some amazing successes. So here is one that I like to show, which is the deep visual semantic alignment for generating image descriptions. So basically, you present the image to the system, and then the system tells you what is on this image. So you see here, the image that was presented received the response from the system: woman in white dress standing with tennis racket, 2 people in green behind her. So pretty impressive. And then I couldn't resist, so I submitted this image for classification. And guess what was the result? The result was, best guess, deep learning image recognition. But there are failures. Centipede, peacock, jackfruit, bubble. The system was 99.6 sure that this is the correct classification. And this is one of the problems with such systems. You know, you can present a nearly random set of pixels to the image, and you will get a response that the system is really confident about certain solution. Look at this, electric guitar or baseball. You would say complete nonsense. And this is the system that was performing so admirably on images like this. So this is one of the problems. So system may tell you it's completely sure about something, but it is not the case. You also have challenges in development, and that is you have uncertainty in development. It's difficult to forecast success. You need to try out things. You may try with different algorithms, try with different data set. Significant problem, the data that you present and the use for training may be biased. The system will be biased as the outcome of that. And one thing that you should never forget is to integrate the AI parts with the conventional, typically big data systems. You should never have your AI system as isolated thing. The other problem is debugging. Something is not right. How are you going to go about this? You know, the system is typically a black box. You cannot go and just fix the bug. For introducing these techniques in the business, you first want to start with data research, build hypotheses, build various solutions, see how they work, And you may want to try it out, do the A/B testing, put some part using one algorithm, some part using the other approach, see how it performs. You want to have a real-world confirmation. In your organization, how do you want to start with this? So first, identify the areas where deep learning and AI can add value. And always view what is the value for the customer. Think about your experiments. You should not hesitate to start experimenting, but you need to have also a long-term goal in picture. And that the worst mistake that people do is they don't get started. They think, oh, this is immature, we are going to do it later. The time is passing by. You have seen already 288 companies in this space. Things are moving very fast. You don't want to get behind. Get your hands dirty. I know most of you are managers. A little bit of Python will not harm you. And if it's difficult, find a curious developer in your company, sit together and say, let's do this TensorFlow, let's classify something. Because only when you start using it, your mind will get activated and you will recognize where else can you apply these approaches. And finally, a set of references for you. This is for the homework for the weekend. Couple of introductions. There is a wonderful little tutorial, visual introduction to machine learning. Superbly done, very easy, great to give you an overview. Columbia University published their course on AI. Now, this course has introduction, which is a set of wonderful videos, and they have programming exercises. For you as managers, you can stay away from the code, but watch the videos. You want to be at least buzzword compliant with all of these things. I already mentioned, in the cloud, you have a variety of services. Choose one that is most convenient for you and try them out. They all have a pretty nice, simple tutorials. And also a couple of other services from other companies, like voice recognition, building bots with which you can have a conversation, a recognition of visual images. And then if you are up to a little bit of programming, check out TensorFlow. It is very easy to start, good tutorials, and quite impressive in its functionality. And the Keras is the layer above it that makes the APIs easier and convenient to use. So that is your homework. I think we are at the end. And questions? Okay, thank you. I'll be around after the talk, so you can join me.